Okay, so the next one is 26. Here we have to prove that this map from the group U16 to itself given by this formula. That is, the mapping takes the input x and gives us the output x cube, where x of course is coming from the group U16. This map we have to prove is an automorphism of this group. And then we have also been asked about the same thing for these two other maps. This one maps x onto the 5th power and the next one maps x onto the 7th power. And then we have also been asked to generalize this situation. So let's see the solution. Let's give the map some name. Let f be the given map. Now, it's pretty easy to show that this f is structure preserving. What we mean by that is this, of course. Since U16 is abelian for any two elements x and y in U16, f of the product xy is of course by definition the cube of xy, but since the group is abelian, this is nothing but x cube y cube, and that is just f of x times f of y. Okay, so a part of showing that this is an isomorphism, we see it here. Now next we have to prove that this map f is 1 to 1 and onto. Now luckily we are looking at a map on a finite set, that too from a finite set to itself, and we know that for such maps it is 1 to 1 if and only if it is onto. So it's enough to show that f is just 1 to 1, that is injective. So we can mention that since this is finite, f is 1 1 if and only if it is onto. So now we will show that f is 1 to 1. So you can either show that directly or you can try to calculate the kernel of it. So let's go for that kernel. Let say z be any element in the kernel of f. If we manage to show that this z has to be equal to the identity element in U16, that is 1, then that means f is 1 to 1. So being in the kernel means what? It means that the f image of z should be the identity element here. Same thing, same group, so 1. Then in fact we can write here itself the actual thing. That means the cube of z, which is f of z by the definition of f, is equal to 1 in U16. So that means in the group U16 the cube of z should be equal to 1. But if you treat this z as an ordinary integer, then what this equality really means is that 16 should divide z cube minus 1. or in other words, z cube mod 16 should be equal to 1. Thus, and then one can just do a simple calculation. You see what are the elements in U16. U16 by definition consists of all the positive integers less than 16 and relatively prime to 16. Since the only prime divisor of 16 is 2, so that means this will consist of all the odd integers, odd positive integers less than 16. That means these are the elements. and 15. Now what one can do is that one can just simply calculate the cubes and calculate modulo 16. That is, to put it more elaborately, for example, if your z is 5, just simply saying, then what you do, you calculate the cube of 5 and then divide by 16. The remainder is this. That will not be equal to 1. Only when you take z is equal to 1, then only you will get 1. For z equal to 1, of course, z cube is 1 itself, and since it's less than 16, so it is the remainder when you divide it by 16. But for other numbers, it may be higher. For example, for z equal to 3 itself, it exceeds 16. It will become 27. But when you divide 27 by 16, you do not get remainder 1. And that will be the case for all the other elements here. And that is why z itself has to be equal to 1. It doesn't look very good because we are just simply blindly calculating with some numbers and finding out that z has to be equal to 1. But let's just go like that simply. So let's write one can verify directly that now, okay, it's entirely up to you to calculate like this, or you may come up with some idea to shorten this calculation. But I don't think it's an extremely long, unimaginably large calculation. You just have to deal with how many numbers? 1, 2, 3, 4, 5, 6, 7 numbers. For 7 numbers, you have to calculate the cube, and in each case, you calculate the remainder when you divide those cubes by 16. So it can be done. So I'm just simply writing one can verify directly that. Okay, let me at least write this much. Not equal to 1 for since one cube mod 16 is 1, we thus have this equal to 1. So that means the only element in the kernel is the identity element. Hence, f is 1, 1. And being 1, 1, we have already mentioned that it is also onto and structure preserving. That means it's an isomorphism. An isomorphism, that too from the group to itself, so that is why it's an automorphism. And the same thing will happen for the other two maps. The one which maps x to its 5th power and the one which maps x to its 7th power, which I leave to you. Okay, again some calculations, because the exponents are larger, there is a little, you will involve some slightly larger calculations, but it can be done. One can similarly show that both the maps this and this are automorphisms of U16. But now comes the important part of this exercise, which is the generalization. What do we see from these examples? From these 3 maps, we see that in each case, the exponent that you see here in these powers, in the outputs, these are odd positive integers. So is it the case that if x gets mapped to a power where the exponent is an odd positive integer, the same thing is going to happen? Actually, that is the case, and that will be our generalization. And for that, of course, we cannot hope to go for a direct calculation, since the exponent will now be arbitrary. So here we will need a trick. In general, we claim that the map, let's give it some other name, G, given by this formula g of x equal to x to the power n is, and you can write isomorphism, but more specifically automorphism of U16 for all odd positive integers n. Now, how to show this? Okay, for that we can go like this. See, structure preservation is just like before. That means you take 2 elements in U16, again x and y. Then because U16 still it is just simply U16, so it is abelian. So g of xy will be equal to g of x times g of y. That is like this. For any x and y in U16, does not matter what n is, g of y. Okay, but now again, because G is a map from a finite set to itself, it's one-to-one if and only if it's onto. So now we focus on showing that G is one-to-one. Let this be any element in the kernel of G. then this is equal to 1. Okay, now find this z is coming from the kernel of G, so ultimately this z is an element in U16. Which element we still don't know. We want to show that it has to be equal to 1, it cannot be anything else. But what are the other things in U16? All those odd integers less than 16 and greater than 1. So let us now see what the nth power of those odd integers can possibly be modulo 16. Let's just see that. Since all of those other elements which may be equal to z, as yet we don't know, okay, they are all odd, so they are of the form 2k plus 1. So we have two k plus 1 for some integer k. Okay. Now here is the thing, what we are first of all going to do, n of course is something, right, some odd positive integer, but let us see what happens to the fourth power of z. The reason will become clear soon. Then, in fact, let us just calculate this. Simple factorization gives us this. So if you substitute 2k plus 1 for z, then you are going, after all expanding the square, you get 4k square plus 4k plus 1 plus 1, that means plus 2, and from here you are simply going to get 4k square plus 4k. So this becomes, you can take 4 common out from this factor and 2 common out from this factor. That gives you 8 outside. 2k square plus 2k plus 1 times, in fact, if you take k also outside, then you are left with k plus 1. Now note one thing, that fine, we have this factor, but let's concentrate on this. It does not matter what integer k is, k times k plus 1 is always even. If k is even, then this factor brings that evenness. If k is odd, then k plus 1 is even, so that brings the evenness. So that means from this part we are going to get another 2, that when you combine with this 8, it will give you 16. Since 2 divides k times k plus 1, we have 16 dividing this entire thing. In other words, 16 divides this, i.e. is equal to 1. Okay, so the fourth power is actually equal to 1. Now, since n is, but we do not really want the fourth power, we need the nth power, but n is odd, and so now when you divide an odd integer by 4, what are the possible remainders? The remainder cannot be 0, of course. Also the remainder cannot be 2. So that means the remainder is either 1 or 3. You of course know the reason. In other words, what I am saying is that this n being odd cannot be of the form 4m or 4m plus 2, because these are not odd integers. Rather, it has to be of the form 4m plus 1 or 4m plus 3. Okay, so that's the thing we are going to use now. N is odd, and so n is equal to 4m plus 1 or n is equal to 4m plus 3 for some integer m. For some integer m. So let's see each of these two cases one by one. Let n be equal to 4m plus 1. Then what is z? Well, we know what z is. Z has been chosen to be any element in the kernel of our function. But now note that z can also be written as this. Why? Because we have already shown that the fourth power of z mod 16 is 1. In other words, in the group U16, the fourth power of z is equal to 1. So that's why in the group we can write in place of z, z times 1. And if the fourth power is 1, then its mth power is also equal to 1. But now using the rules of exponents, which are true in any group, this is but because your z is coming from the kernel, so this nth power is 1. So that's how you have proved that z itself has to be equal to 1, and that's what we want. On the other hand, if n, so this is one of the cases, if n is 4m plus 3 instead, then similarly you have this. But in that cube calculation, you have already shown that the only cube in U16 that can be 1 is 1 cube. No other element's cube is equal to 1. But then again z must be equal to 1. So in any case, this is equal to 1. Thus g is 1, 1. Regardless of what that exponent n is, its oddness and everything else combined gives us this fact that g is 1, 1, and hence is an automorphism of U16. So that is our generalization. So you see that even in this general case, we had to rely on that cube calculation. So that part we have to do at least, even if we don't do the 5th power and 7th power calculations, because now This itself takes care of those things, but at least the cube calculations have to be done. But anyway, that is the solution. Now we are going to go to the next one. Let R be an element in the group UN prove that the mapping alpha from Zn to Zn. So you see, carefully see that this is one group, this is an entirely different group, okay, the Zns. And the rule for the mapping is this. Defined by alpha of S equal to Rs, or is that same thing, modulo n, of course, because we want the output to be here, is an automorphism. So here also the situation is similar in the sense that you are still having a function from a group which is a finite set to itself. So to show that this function is a bijection, it's enough to show that it is one-to-one, and that's what we will do. So let us first show the structure preservation. Let say S and T be two elements in the modular group. Then keep in mind, now the operation is addition modulo n, so we will use the plus symbol. Then alpha of S plus T, by the definition of alpha, is S plus T times R mod n. But from elementary properties of arithmetic of remainders, we have already seen these things before, okay, when we dealt with integers. If you remember, this is nothing but SR mod n plus TR mod n. But before we just simply write like this and complete the calculation, let's just see for once what this even means. Okay, it means that S and R are, well, you can think of them as ordinary integers. You multiply them, okay, and the product you divide by n, you will get a remainder. This is that remainder. This symbol represents that remainder. So from that you can now understand the meaning of these things, and it's a property of those remainders. Sometimes it gets confusing. I mean, when should we treat elements in Zn or Zn as congruence classes, and when should we treat them as ordinary integers? To get rid of this confusion, some people do not use these symbols. For example, in this group, we understand what we mean by one being in this group. Actually, this one is not an integer, not the integer one, but rather the congruence class modulo 2 containing 1. More specifically, it is the set of all odd integers. However, in this group, it behaves like the ordinary integer 1. Okay, so that's why, in some sense, and that is why we use the symbol 1 for the integer as well as for this element in Z group. But we should always be aware of the distinction. Anyway, so let's just get back to business. So this is alpha of S plus alpha of T. Next, same, you assume an element in the kernel of alpha. Let U be any element in the kernel of alpha. Then alpha of U will be equal to the identity element in this group, which is 0. 0 is equal to alpha of U, which by the definition of alpha is U r modulo n. And the actual meaning of this equation is that n divides UR, the ordinary integer UR. And after this, you have to use this fact. Since R is coming from the group UN, so by definition of UN, R is a positive integer less than n and relatively prime to n. That relatively prime part is important. That means the greatest common divisor of R and n is equal to 1. So you know from properties of integers, this one has a name also. I think it's called Euclid's lemma. Since these two are co-prime to each other, so they do not have any common factor other than 1 and minus 1, of course. So n cannot divide R actually. N has to divide, well, even if n divides R, n in that case n has to be either 1 or minus 1, but in that case n also divides U, and if n is greater than 1, then n does not divide R, so n has to divide U. In any case, n has to divide U. But in our group Zn, what does this divisibility mean? It means that U has to be 0. So that means the only element in the kernel of alpha is the identity element. So that's why alpha is 1 to 1, and taking everything into consideration, alpha then has to be an automorphism. Okay, so that is the solution. Is there anything else? No, that's the solution. And let's now see one more. And for this next one, I will just give you the hint. It's very easy. If I give you the function, you will understand. To which familiar group is this group? It's the group of these matrices. Where A varies over the set of integers, isomorphic. And there is a second part also. What if Z is replaced by R? Okay, so here is the thing, here is the hint. You set up a function from the additive group of integers to this group. To this group means if you call it G, you give it some name, and the function is just simply this. F of A is this matrix. This is an isomorphism. This is going to be an isomorphism. At least let me show you that this is structure preserving. Keep in mind that this is a group under matrix multiplication. Although the entries are integers, but the thing is matrix multiplication. The author hasn't explicitly said anything, but you can understand that this is matrix multiplication. What else can it be? Matrix addition. But this set will not be closed under matrix addition. If you add any two such matrices, the diagonals will become 2. So that loses the form. So it has to be multiplication. So what I am saying now is that if you take two integers A and B and say you calculate f of A times f of B, then it will be 1A01, 1B01. To perform the multiplication, 1 times 1 is 1 plus A times 0 is 0, so 1. B plus A, and B plus A is actually A plus B. 0 plus 0 is 0, 0 plus 1, 1. So you see that this is nothing but f of A plus B. So that's why this function preserves structure. And then obviously this is onto, and one-to-oneness also is almost obvious. So in fact I have shown everything practically, that f is an isomorphism. Do not write automorphism here, okay, because the two groups are different. So that is why this given group is isomorphic to the familiar group of integers under addition. Now if you replace integers by real numbers, same thing. In that case the group will be isomorphic to the group of real numbers under addition, which is also a familiar group. So that's just it. And let me just end the video here itself. Tomorrow again we have our usual analysis upload. So see you tomorrow. We are going to see what comes next. Right now we are doing those things, closure, adherent points. So we will see what comes next. So see you tomorrow with those things in analysis. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.